ladies and gentlemen. Today we're talking about section 4.4, which is we're proving triangles congruent by two shortcuts. We talked about side, side, side in section 3. Now we're going to talk about side, angle, side, and the hypotenuse-leg shortcuts. The first one is a postulate, the side, angle, side congruence postulate, which states that if we have two sides and the included angle of one triangle congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. The included angle is just the angle that's between the two sides, or formed by the two sides. So with this case down here, we have SRT, where this angle is formed by these two sides, and VUW, where this angle is formed by these two sides. So these two triangles would be said to be congruent. As an illustration of that, the only way I can complete this angle to make it a triangle is bring a side down here. Over here, no other triangle is possible except bringing this side down here. So our two triangles are forced to be congruent because those are the only possible sides I can draw, which are the exact same side from S to T and V to W. So it is a postulate. There is no formal proof for it. It's something that's assumed to be true and taken on fact by faith. Let's look at a proof where we use this postulate to prove something. So for this proof, we're given the fact that segment BC is congruent to segment DA, which is marked here, and we're also given that segment BC is parallel to AD, given by these arrows. Now, one of these talks about segments being congruent, and one talks about lines being parallel. Since they're two different things, following this person's train of thought, they kept them different steps, and both of them are given. You can keep them together as one statement and one reason, but this person decided to keep them separate because this is our first side, and this doesn't necessarily tell us anything about sides. Parallel lines are more useful for angles. So if we have two lines parallel, then we have special angle pairs formed here. We have, if these are our two parallel lines, we have a transversal. Because we have a transversal, we have special angle pairs are formed like alternate interiors. So these alternate interior angles are going to be congruent because our lines are parallel. So that gives us our angle that we needed. We can also tell in this proof that we have a shared common side, AC. In this case, we'll say that AC is congruent to itself with the reflexive property. The order of the letters doesn't matter in the segments, so it's still considered the reflexive property because something is still congruent to itself, just a different ordering of the letters. Because AC in one triangle, since these are rotated, would be CA in the other one if we were to separate these and rotate these. That's a pair of corresponding sides. So in this case, we have side, angle, side, and side, angle, side. Our angle is included between the sides we're using here, so we can use our side, angle, side congruence postulate to say that these two triangles are indeed going to be congruent. So there's a quick proof where we're using it, and remember that if you're using side, angle, side, the angle is in between the two sides, it's formed by the two sides, it's the included angle. Looking at something that involves other concepts in geometry from other sections, in other chapters, we're going to use some information about circles. In the diagram, segment QS and RP pass through the center M of the circle. What can you conclude about these two triangles? Well, if M is the center of the circle, then all of these segments are considered to be the radius of the circle. They go from the center to the actual edge of the circle itself. So since all of these are the radius of the circle, the radius is always going to be equal. Any of those will have the same measure because they're all the radius, and the circle only has one radius, so the radius doesn't change. Therefore, all these are congruent to each other. We also know that these are vertical angles because they're formed by two lines intersecting in that X formation, and they're across from each other. So in this case, we have side, angle, side, side, angle, side. So we know that these two triangles are going to be congruent. Now, it does not say we have to explain or justify our steps, so this is all we need to write, but as a rule, you will see in the directions, you'll have to be justifying your steps and giving explanations. Since that's the case, here you would talk about the radius, giving you congruent sides, vertical angles, giving you your included congruent angle, and therefore you can use side angle side because you have two sides in the included angle. So there's kind of a more of a cross concept problem because we're going with different geometric concepts. Our second concept today is actually a theorem because there's a proof of it somewhere, and this theorem is proved in example 37 on page 439 with the worked out solution on page 932. So it's the hypotenuse-leg congruence theorem. It states if the hypotenuse and the leg and a leg of a right triangle are congruent to the hypotenuse and the leg of a second triangle, we know the two triangles are congruent. This only works for right triangles. So it has to be a right triangle for us to be able to use this. If we have the hypotenuse congruent, which remember the hypotenuse, if you remember from previous math courses, is always across from your right angle, and it's the longest side in your triangle. If the two hypotenuse are going to be congruent, and we can just get one of our other sides, which are called legs in a right triangle, we can have one pair of legs congruent, and that's enough to say the two triangles are. It only works if we're dealing with a right triangle. So let's use this in a proof. Here, we have some given information, and we have two triangles overlapping, forming three smaller triangles. We want to prove that triangle WYZ is congruent to XZY. Well, since WYZ and XZY are our two large triangles that are overlapping, I'm going to pull these apart and make them separate so it's a little bit easier to look at. And then I'll label these accordingly. So this was W, Z, and Y. This was X, Z, and Y. And using our given information, we're told that a couple of segments are congruent. We are told, and do this in red, that WY and XZ are congruent. That's given to us. And again, this particular person whose train of thought we're following separated our given information because one talks about congruence, one talks about perpendicular. So they're different concepts, so they use these as different given steps. Now, if these sets of lines are perpendicular, we can conclude some information about them. Because remember, we can't use HL unless we know the two triangles are right triangles. So we have to show that they're right triangles first. Well, right triangles always include right angles. And since these lines are perpendicular, we know they form right angles. So we can say those two angles are right angles, and that's our definition of perpendicular lines, which states that if two lines are perpendicular, they intersect to form right angles, or a right angle. So that's how we have it in this case. And since they are right angles, we know that these two triangles are right triangles, since they're triangles with right angles, and that's our definition of a right triangle. So first of all, since these are right triangles, we know that these sides that are congruent are our hypotenuse because they're across from the right angle. So we have our H. We still need to show that a leg, or a pair of legs, corresponding legs, are congruent. So either our short legs or our long legs. We had to show, though, that this was a right triangle. If it was given to you, you could use it as given that it's a right triangle. Otherwise, you have to show within your proof that the triangles are right. Otherwise, you cannot use HL. Well, to show that a pair of legs are congruent, we have the same segment, ZY, in both of these two triangles. It's a shared common side. On one triangle, we call it ZY, and one triangle, we'll call it YZ, to make sure that our order of our letters are correct. And we use our reflexive property because we're saying it's congruent to itself. Even though the letters are out of order, it's still the same segment. So that's our reflexive property. Something is congruent to itself. And since we have H, and now we have our pair of legs, we can use our HL congruence theorem to say that our two triangles are congruent. If you're dealing with right triangles and proving them congruent, you have the option to use HL, but if possible, you could also use side, 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 or side, angle, side. You're not necessarily limited to using just HL. In this case, we had to use HL. In some cases, you might not have to. This concludes a brief overview of section 4.4. Questions, as always, I'll take in class, and I hope this video helps a little bit, especially if you're absent. This is a great way to get caught up.